Что он там работает? Сейчас посмотрим. Работает отлично. Okay, so at the previous lecture we introduced the GNS construction, which manufactures representations of C-star algebras out of positive functionals. Well, let's now briefly recall the construction itself, the GNS construction. Just a short summary of this construction. GNS is for Gelfand-Naimark and Siegel. So we start with the C-star algebra. A is a C-star algebra and the positive linear functional f on A. F is positive. And we define a semi-inner product on A by the following rule. This is a semi-inner product. Semi-inner means that this is something like an inner product. The only difference is that if A is non-zero, then in principle it can happen that the inner product of A by itself is 0 sometimes. But this is the only difference between inner products and semi-inner products. In particular, this semi-inner product defines a semi-norm on A by the following rule. Square root of this number, and we can make this semi-inner product into an inner product on a suitable quotient of A. So we define by NF, we denote by NF the set of those elements in A where this semi-norm vanishes. And by using the Pirkovskiy-Schwarz inequality, we observed that the same subspace can be interpreted as follows. It consists of all elements A such that f of BA is 0 for every B in our algebra. Or equivalently, this is the set of those elements A such that f of A star B is 0 for every B. So then we consider the quotient of A modulo this subspace, and we get an inner product on this quotient given by the following formula. So the inner product of two elements in the quotient is just the semi-inner product of their representatives. This is an inner product on the quotient. So the quotient becomes an inner product space. We denote it by HF0. This is the quotient equipped with this inner product. And then we observe that NF is actually a left ideal in A. This follows from this formula. So the quotient becomes a left module over A, and we get a representation of A on this inner product space. So we denote this representation by pi f0. So pi 0 of A is just the left multiplication operator. Pi f0 of A takes B plus NF to AB plus NF. Well, HF0 is not necessarily complete. It's just an inner product space. But we can consider the completion of HF0. We denote it by HF. So HF is a Hilbert space. And so far, all this construction makes sense for an arbitrary star algebra and an arbitrary positive functional on this algebra. So the norm on A wasn't involved. But we proved that if A is a C-star algebra, then the separator is actually bounded. Actually, it is bounded. Its norm is less than or equal to the norm of A. And so it uniquely extends to the completion. So we get an operator pi f of A on HF. And as a result, we get a star representation of our algebra A on HF. And we call it the GNS representation. GNS representation of A associated to F. Let's also recall that GNS representations can be characterized in abstract terms. So we have a map lambda f from A to HF, which takes every element A to its coset modulo NF. And we observe that this map has the following properties. First of all, its range is dense in HF. Second, the inner product of lambda f of A and lambda f of B is just f applied to B star A. And finally, our representation pi f of A acts on the elements of the form lambda f of B by the following simple formula, lambda f of AB. So these properties are just immediate from our construction. And actually, these properties can be used to give an abstract characterization of GNS representations. Namely, by an abstract GNS representation, we mean a triple H, pi, and lambda, where pi is a star representation of A on a Hilbert space A, on a Hilbert space H. And lambda is a linear map from A to H, which satisfies all these conditions. And then we observed, finally, at the end of the lecture, we observed that if we have such a triple, then actually we have a unitary isomorphism between H and HF. So this is a unitary isomorphism of A modules. And moreover, there is a unique unitary isomorphism of A modules, which is compatible with the map lambda in the following sense. So this diagram commutes. There is a unique unitary isomorphism between these modules such that the diagram commutes. Sometimes this is convenient because instead of constructing HF explicitly, sometimes we already have some concrete representations, some concrete representation and some concrete map lambda. And if these conditions are satisfied, then we automatically get that this representation is actually isomorphic to GNS representation. By the way, let's also observe that this map lambda f is contractive. Because if we substitute here A, then we get the norm of lambda f of A squared. So we substitute A here, we get this. So this is f applied to A star A. And if we assume that f is a state, then this is less than or equal to the norm of A star A. If f is a state. That is, if the norm of f is 1. And by the sister axiom, this is just the norm of A squared. So as a result, we see that the norm of lambda f of A is less than or equal to the norm of A. So lambda f is contractive. It doesn't increase the norm. Okay, so this is a short summary of GNS representations. And now we are actually one step away from proving a fundamental result. in sister algebra theory, namely the second Gelfand-Naimark theorem, which states that every sister algebra can be faithfully represented, and so can be isometrically represented as an operator algebra on a Hilbert space. So every sister algebra is actually an operator algebra. Before proving this result, let's make a short digression and let's discuss summable families. Summable families and Hilbert direct sums. So suppose we have a normed space. X is normed space. A set, an arbitrary set I, and a family of elements in our space X. A family of elements of X indexed by our set I. So roughly what we want to do is to make sense of the following expression. So in general, I is not assumed to be countable. So what does that mean? To answer this question, let's consider this the collection of all finite subsets of I, we denoted by fin of I. This is the family of all finite subsets of I. And we observe that this is actually a directed set, a directed partially ordered set. The order relation is just the inclusion. It is obviously directed because if you have two finite sets, then each of them is dominated by their union, which is also finite. So it is a directed poset. And now we construct a net indexed by this poset. So for every finite subset J of I, we denote by xj the sum of the elements xi, where I runs over J. So this is just a finite sum. And we say that the family xi is summable if this net converges. If this net converges in X. And the limit of this, we denote by the sum of our family, the limit of this net. So by definition, the sum of our family is just this limit. This is a formal definition of a summable family and of the sum of this family. The following exercise shows that actually summable families can be defined in more elementary terms, which don't involve nets. So I claim that our family is summable. If and only if it satisfies the following two conditions. First of all, the set I0 of those indices I for which xi is not 0 is at most countable. So in other words, our family is essentially countable. So it is supported on the most countable set. And second, if it is finite, then, oh, by the way, let me, let's also introduce a special notation for the sum of this family. So this family is summable to an element little x, if and only if I0 is at most countable, and if it is finite, then the sum, which is, this is a finite sum, is equal to x. And if it is infinite, if I0 is infinite, so it is strictly countable, then for every bijection between the natural numbers and I0, that's denoted by phi, for every bijection phi between the natural numbers and I0, the following series, sum x phi of n, converges to x. So this is equivalent to the summability of our family to little x. So in other words, if we look at these conditions, we see that basically summable families are equivalent to unconditionally convergent series. Unconditionally means that this is true for every bijection. So this doesn't depend on how we how we use the numbering for our elements. But nevertheless, in practice, it turns out that in many situations it is more convenient to work with this abstract definition of summability rather than with unconditionally convergent series. In the case where our family consists of non-negative numbers, the summability condition can be simplified. This is also a rather simple exercise. Suppose that, say, AI is a family of non-negative numbers, of non-negative real numbers. Then I claim that this family is summable. If and only if the following supremum is finite. Supremum of all finite sums AI, where the supremum is taken over all finite subsets of I. If and only if the sums of, if only of arbitrary finite sums are bounded by a common constant. And moreover, in this case, if this is true, then the sum of our family is equal to this supremum. The supremum is just the sum of our family. And in this case, we usually write the following combination of symbols. We just say that the sum of our family is finite. Meaning that this supremum is finite. But the exercise shows that this condition is equivalent to the summability of our family in the sense of this definition. Okay, let's now discuss Hilbert direct sums. Suppose that we have a family Hi of Hilbert spaces. A family of Hilbert spaces. And let's denote by H the set of those elements xi in their product. This is just the product of HIs as vector spaces. for which the following sum is finite, in the sense of our previous definition. That is, this family is summable. It's a simple exercise to show that H is not just a set, but is actually a vector subspace in the product. H is a vector subspace of the product. And moreover, it's actually a Hilbert space. H is a Hilbert space with respect to the inner product given by the following formula. If you have two such families, two such square summable families in the product, then we define their inner product to be the following sum: xi, yi. So I claim that this family is summable, and its sum determines an inner product on this space, and it is complete. Well, the only point which is not entirely obvious is the completeness of H with respect to this inner product, but the proof is almost identical to the proof of the classical well-known fact that the space little L2 of square summable sequences is complete. So I'll leave this as an exercise for you. And the space, now we have the following definition: the space H is called the Hilbert direct sum. Hilbert direct sum of our family HI. And we use the following notation. So we write the usual symbol for the direct sum, and we put a dot over this symbol in order to distinguish between this operation and the algebraic direct sum. So the algebraic direct sum consists of all finitely supported families. So this is bigger than the algebraic direct sum. This construction is easily extended to star modules over star algebra, over C star algebra. So we have the following proposition. Suppose that A is a C star algebra, and HI is a family of star modules over A. Then I claim that their Hilbert direct sum is also a star module over A with respect to the following action. If we have a square summable family xi, and we want to define this element, then this is just the family AXI. Well, the only point here which is not immediate from the definition is the fact that this family is also square summable. But this is very easy because we actually have the following estimate. The norm of AXI is less than or equal to the following product, the norm of A times the norm of xi. And this is true because every representation is contractive. If we denote by pi I the respective representation of A, then its norm is less than or equal to 1. Well, we know that every star homomorphism between C star algebras is contractive. So the norm of the respective representation is less than or equal to 1. This implies that we have this inequality, and therefore this readily implies that the family AXI actually belongs to the Hilbert direct sum. And now the axioms of a star module are readily verified. So the Hilbert direct sum of a family of star modules is also a star module. Let's also introduce the respective notation for representations. If we have a family of star representations pi I, a family of star representations of I of A, then we denote by the following combination of symbols. The representation, the star representation of A, associated to the respective module, where HI is just the space where pi I acts. So pi I is a representation of A on HI. So HI is an A module. We take the Hilbert direct sum. And the respective representation of A will be denoted like this. And it's called the Hilbert direct sum of the representations pi I. Hilbert direct sum of the family pi I. Let's observe, well, actually this is a simple exercise, that for every element A in our algebra, the norm of this operator, so we take the direct sum, the Hilbert direct sum of our representations, and apply this representation to A, so we get an operator on the space. And I claim that the norm of this operator is just the supremum of the norms of pi I of A. This is rather elementary, so this is an exercise for you. In practice, Hilbert direct sums often appear in the situation where all the modules HI are actually closed and pairwise orthogonal submodules of some fixed star module over A. And the next exercise describes this situation. So suppose that H is a star module over A, and HI is a family of closed and pairwise orthogonal submodules of H. Then I claim that there exists a unitary isomorphism between their Hilbert direct sum, HI, and the closure of their algebraic sum in H. So we take the algebraic sum. This is also a submodule, not necessarily closed. We take the closure, and the resulting submodule will be isometric, will be unitarily isomorphic to the Hilbert direct sum. Now this isomorphism is given by the following explicit formula. It takes the square summable family Xi in the Hilbert direct sum to the sum of this family. So this exercise implies that in the case where all the modules HI are like this, so they are pairwise orthogonal closed submodules of H, then their Hilbert direct sum is just the closure of their algebraic sum. It is also contained in H. So if, in this case, if the algebraic sum is dense in H, so we have this equality, then we say that H is just the Hilbert direct sum. Is the Hilbert direct sum of our family, and we write the following equality. So formally, H, of course, is just isomorphic to this Hilbert direct sum by means of this concrete isomorphism, but in practice, we often write this equality, and usually this doesn't lead to any problems. Okay, so now we are ready to introduce the so-called universal representation of a C-star algebra, and to prove the second Gelfand-Naimark theorem. So again, we have a C-star algebra A. A is a C-star algebra. And let S of A denote the set of all states. The set of all states on A. That is the set of all positive functionals of norm 1. We define the universal representation of A as follows. We denote it by omega A, and this is just the Hilbert direct sum of all GNS representations associated to all states of A. Unfortunately, I cannot explain you why this representation is called universal. In fact, this representation indeed has some universal property, but to understand what this property is, we would have to learn the basics of von Neumann algebras, and this would take several lectures. So we simply cannot afford this. But for our purposes, this representation is important because it leads directly to the following fundamental result, to the second Gelfand-Naimark theorem. The theorem states that every C-star algebra A has a faithful, or equivalently an isometric, star representation on the Hilbert space. And more exactly, I claim that the universal representation is faithful. Omega A is faithful, or currently isometric. In this case, these two notions are equivalent because we remember that every injective star homomorphism between C-star algebras is isometric. The proof of this theorem will be almost immediate from the following lemma. The lemma states that for every element A in our algebra, there is a state S F on A such that we have the following inequality. The norm of pi f of A is equal to the norm of A. So first we prove the lemma. Proof of lemma. For convenience, we can assume that A is the norm of A is 1. Clearly, everything is reduced to this case. Otherwise, we just divide A by its norm. And we look at, so we take two elements B and C in A, and we look at the following inner product, pi f of A, applied to lambda f of B, and we take the inner product of this vector with lambda f of C. Why is it natural to consider this expression? Well, these vectors, this one and this one, run over a dense subspace in our Hilbert space. So the norm of pi of A is just the supremum of this expression, or not of this expression, of the absolute value of this expression, as these two vectors run over the unit sphere. But what can we say about this expression? We recall that this is just lambda of AB. This is lambda of AB. And so by just by the definition of the inner product, this is f applied to C star AB. Now let's choose concrete elements B and C. We let C equal A, and B is A star A. So in this case, if we take such elements B and C, then C star AB is A star A, A star A. That is A star A squared. And now we recall an important result, which was proved some time ago, that for every normal element, we can always find a state such that the state evaluated at our element gives us the norm of this element. So we can choose a state f on A such that f applied to A star A squared gives us the norm of this element. This element is normal, so our result applies. We can find such a state. And this element, well, its norm by the C star axiom is, if we apply the C star axiom twice, then we get this norm as 1, because the norm of A is 1. Therefore, if for these elements B and C, we see that this number is 1. Pi f of A, lambda f of B, the inner product with lambda f of C, is equal to 1. But on the other hand, this is less than or equal to the norm of pi f of A. For convenience, I take the absolute value here. So it is less than or equal to the norm of pi f of A just by the Cauchy-Bonyakovsky-Schwarz inequality. Because these two vectors, lambda f of B and lambda f of C, they are also in the unit ball of the respective Hilbert space. Well, A is in the unit ball of A, C is also in the unit ball of A, B is also in the unit ball of A, and we know that lambda f is norm decreasing. So these two elements are in the unit ball. And now the Cauchy-Bonyakovsky-Schwarz inequality gives us this. And we deduce that the norm of pi f of A is greater than or equal to 1. Well, the opposite inequality is clear because pi f is non-decreasing, it is contractive. And so as a result, we deduce that the norm of pi f of A is equal to 1. That is, to the norm of A. And this completes the proof of our lemma. Now, the proof of the Gelfand-Naimark theorem is just a line. So, omega of A, the norm of this operator, omega is the Hilbert direct sum of all GNS representation associated to all states. So this is the supremum of pi f of A, of the norms of pi f of A, where f runs over the collection of all states. But now our lemma implies that this is greater than or equal to, in fact, is equal to the norm of A by lemma. And so this readily implies that omega is isometric. Well, maybe it will be more understandable if I write the equality here. Clearly, it is less than or equal because, well, pi f is contractive. But it is exactly the norm of A by our lemma. And that's it. So this completes the proof. So in summary, we see that every C-star algebra is in fact an operator algebra, which is very useful. In general, the Hilbert space, which appears in the construction of the universal representation, is huge. So we take the Hilbert spaces associated to all possible GNS representations, and then we take their Hilbert direct sum. Usually, this space is not separable. Even if A is separable, this direct sum is not separable in the general case. But nevertheless, if A is separable, then we can construct a faithful representation in a more optimal way, and this is a useful exercise. Suppose that A is a separable C-star algebra. A separable C-star algebra. Then, first of all, I claim that all Hilbert spaces HF are separable. HF is separable for every state. And moreover, we can choose a state F on A in such a way that the GNS representation pi f is already faithful. So, in other words, to get a faithful representation of a separable C-star algebra, there is no need to take the sum of all GNS representations. It's enough to take only one of them for a suitable f, and it will be faithful. So, as a result, a separable C-star algebra can be faithfully represented on a separable Hilbert space. Okay. Now our next goal will be to understand that GNS representations actually play the role of building blocks for arbitrary representations of C-star algebras. So towards this goal, we will discuss non-degenerate representations, and cyclic representations. So suppose that A is a C-star algebra, and that H is a star module over A. We say that H is essential, H is essential or non-degenerate if it satisfies the following condition. If the closure of AH is equal to H, where AH is just the linear span of all elements of the form AX, where A runs over A and X runs over H. So clearly AH is a submodule in H, but not necessarily closed. So we take the closure, and if this closure is exactly H, then we say that H is essential or non-degenerate. And the same terminology applies to representations. The only difference is that when we work with modules, we usually call them essential. And for representations, the more common term is non-degenerate. But in principle, they are synonyms, essential and non-degenerate. In the general case, this submodule, which is in the general case it is a proper submodule, is called the essential part of H. And we denote it like this. This is the essential part of H, or the essential submodule. So H is essential if and only if it's essential, its essential part is equal to H. It's natural to conjecture that the essential part is always essential. Otherwise, the terminology is not very reasonable. And this is indeed the case. This is indeed the case. We have the following simple proposition. The essential part of H is an essential star module. So the proof is based on the fact that A has an approximate identity. So let A squared denote the linear span of all elements of the form AB, where A and B run over A. And I claim that this subspace is dense in A, just because A has an approximate identity. So this readily implies that every element is approximated by such products. Now, if we want to prove that the essential part is indeed essential, so we must look at the closure of this submodule, and we want to prove that this is exactly the essential part. So what is this? Explicitly, this is 8, A multiplied by A multiplied by H. We take the closure here, and we take the closure here. Now, by the continuity of the multiplication, by the continuity of the action of A on H, we can just remove this closure over AH. So we get this just by continuity. And for the same reason, we can now take the closure here, and the result will be the same, again by continuity. But we have already observed that this subspace is exactly A. So we get this. And this is nothing but the essential part. And so we conclude that the essential part is an essential submodule. Moreover, I claim that the action of A on the orthogonal complement of the essential part is trivial. The action of A on the orthogonal complement is trivial. Trivial means that it is the zero action. We have AX is 0 for every A, and for every X which is orthogonal to the essential part. Well, the proof is very easy. We simply calculate the inner product of AX by itself, assuming that X sits in the orthogonal complement to the essential part. We move A from here to here, so we get the inner product of X and A star AX. But A star AX sits in the essential part just by the definition of the essential part. And X is orthogonal to the essential part. So as a result, this is 0. So AX is also 0. So as a result, combining these two propositions, we see that every star module is decomposed as the orthogonal direct sum of an essential module and a trivial module. So in some sense, every star module is reduced to essential star modules. The essential part can also be characterized in terms of approximate identities. We have the following proposition. Suppose that E lambda is an approximate identity in A. As usual, we assume that it is bounded by 1 and positive and monotone. Then I claim that the essential part of H consists exactly of those elements X in H such that X is equal to the limit of E lambda X. This is an equivalent characterization of the essential part. The proof is based on a simple functional analytic lemma. Suppose we have two Banach spaces, E and F, Banach spaces, and suppose that T lambda is a bounded net of bounded linear operators from E to F. And suppose that there exists a total subset M of E. Total means that its linear span is dense. The linear span of M is dense in E. Such that for every X in this set M, there exists a limit of T lambda X in F. So T lambda converges pointwise on M. Then I claim that there exists a bounded linear operator T from E to F such that T lambda X converges to T of X for every X in E. So in other words, the pointwise convergence of a bounded net on a total set implies the pointwise convergence everywhere. And moreover, it converges pointwise to a bounded linear operator. The proof is a simple exercise in functional analysis. Now we can easily prove our proposition. Proof of proposition. So we want to show that, we want to prove this equality. It's clear that the right-hand side is contained in the left-hand side. So if X has this property, then clearly it belongs to the essential submodule. So this inclusion is clear. And to prove the opposite inclusion, we observe that we have the following convergence. X equals the limit of E lambda x. If X is of the following form, if X has the form AY for some A in A and Y in H. Well, indeed, if we substitute A, Y here, we see that E lambda A converges to A, and so the limit will be equal to A, Y. So for such elements, the equality is clear. But on the other hand, such elements, the linear combinations of such elements are dense, so elements of this form are total in the essential part. So our lemma implies that the same is true for all elements in H in the essential part. The same is true for every element X in the essential part. And this completes the proof. Okay, let's now introduce cyclic modules, or equivalently cyclic representations. Again, we suppose that H is a star module over A, and let little x be an element in H. We define the cyclic submodule of H generated by X as follows. This is just the closure of all elements of the form AX, where A runs over A. So clearly this is a closed submodule of H. In general, I don't claim that X, the vector X itself belongs to this submodule. Indeed, we don't assume that A is unital. And moreover, even if it is unital, we don't assume that the identity of the algebra acts as the identity transformation of the module. So in general, we don't assume this equality, even A is unital. Moreover, A is not assumed to be unital. So in general, I cannot claim that X belongs to the submodule, but this is indeed the case if we assume that X sits in the essential part. So we have the following proposition. If X sits in the essential part, then it belongs to the cyclic submodule generated by X. A proposition. And this is immediate from this equality. X is equal to this limit, and this limit obviously belongs to the cyclic submodule generated by X. We say that the module H itself is cyclic if there exists an element x in H such that the cyclic submodule generated by x is equal to H, you will have this equality. And each such element little x in H satisfying this condition, of course I don't claim that it is unique. There can be many such elements. Each such element is called a cyclic vector. It's a cyclic vector for H. Now we can easily prove that every non-degenerate representation, every essential representation, can be decomposed as a Hilbert direct sum of cyclic representations. Every star module over A is unitarily isomorphic to Hilbert direct sum of every non-degenerate, sorry, I forgot to write this explicitly, every non-degenerate star module is isomorphic to a Hilbert direct sum of cyclic of closed of cyclic submodules, of cyclic star modules, which are actually contained in this module. The proof is a simple application of Zorn's lemma. So we denote by M the following set. M consists of families of non-zero, cyclic, families of non-zero cyclic pairwise orthogonal submodules. Submodules of H. So M can be made into a pose set. So the order relation is just the inclusion. And it's easy to see that M satisfies the conditions of Zorn's lemma. Well, indeed, which is elementary. If we have a chain consisting of such families, so each element of a chain is a family of pairwise orthogonal cyclic submodules, then we may just take the union of this chain. And this will be, again, a family of the same form, which dominates each family in our chain. So the conditions of Zorn's lemma are satisfied. And so there is a maximal element. Let's denote the respective family by HI. A maximal element of M. I claim that this is exactly the family we are looking for. So let's denote by H0 the closure of their algebraic sum. To prove that H is isomorphic to their Hilbert direct sum, it suffices to show that H0 equals H. We know that in this case we get an isomorphism between the Hilbert direct sum and H. Well, let's assume that this is not the case. assume that H0 is a proper subspace of H. Then we have the following direct sum decomposition, H0 plus H0 orthogonal. I claim that H0 orthogonal is also a submodule. H0 is obviously a submodule. This is the closure of an algebraic direct sum of submodules, so this is a submodule. I claim that the orthogonal complement is also a submodule. By the way, for convenience, let's write a short lemma, because this observation is elementary, but it is quite important. If H is an arbitrary star module over a C-star algebra, and H0 is a submodule, then the orthogonal complement is also a submodule. Is also a submodule. The proof is just a line. We take an element X in the orthogonal complement, an element A in A, and an element Y in H0, and we look at the following inner product, AX and Y. So to show that AX sits in the orthogonal complement, we must show that this is 0. But this is equal to the inner product of X and A star Y. And A star Y belongs to H0, because H0 is a submodule. And X is orthogonal to H0. So this is 0. And as a result, we see that AX belongs to the orthogonal complement. So the orthogonal complement is also a submodule. So this completes the proof of our lemma. Now we can come back to the proof of our theorem. We have this decomposition. We already know that the orthogonal complement is a submodule. We assume that it is non-zero. So we choose an arbitrary non-zero element in the orthogonal complement. And we observe that in this case, if we take our family Hi, which is a maximal element in the set M, and add a single element, namely the cyclic submodule generated by X, then this bigger family is also an element in M. Why is it so? Well, this one is a cyclic submodule. It is non-zero. Why is it non-zero? Because it contains X. So we assume that H is non-degenerate. And for non-degenerate modules, every element belongs to the cyclic submodule generated by this module. It follows from this proposition. So as a result, we see that this submodule is non-trivial, it is non-zero, and it is orthogonal to this family because the orthogonal complement is a submodule as well. So we see that this is also an element of M, which is clearly bigger than our maximal family, and this is a contradiction with the maximality of our family. This contradicts the maximality. So as a result, we conclude that actually H0 is equal to H. H0 is equal to H, and so H is isomorphic, unitarily isomorphic to the Hilbert direct sum of the family Hi. And this completes the proof. Okay. Our next result little theorem, shows that actually every cyclic representation is isomorphic to a GNS representation. Suppose that pi is a cyclic star representation of A on Hilbert space H, a cyclic star representation, and let little x be a cyclic vector for this representation. We define a functional f on A by the following formula. F of A is the inner product of pi away x and x. I claim that, first of all, f is positive. Second, the norm of f is equal to the norm of x squared. And finally, part 3, there is a unique unitary isomorphism. Let's denote it by U, from H to HF, unitary isomorphism of A modules, such that it takes pi of AX to lambda f of A for every A. Well, part 1 is clear, because if we calculate f of A star A, we substitute A star A there, we move pi away star from here to here, and we get pi of AX squared. And this is non-negative. So f is positive. Part 2. Well, clearly, we have the following inequality. The norm of f is less than or equal to the norm of x squared. This follows from the Cauchy-Bonnikovsky-Schwarz inequality applied to our definition of f. And we also use the fact that the norm of pi is less than or equal to 1. Because the norm of pi is less than or equal to 1. So we want to prove the opposite inequality. So let's choose an approximate identity in lambda, an approximate identity in A. Our representation is cyclic. In particular, it is non-degenerate. So we have the following convergence. Pi of E lambda x converges to x. This was one of our earlier propositions. This is true for any non-degenerate star module. If we now substitute it here, we see that the right-hand side converges to the norm of x squared. So we conclude that f of E lambda converges to the norm of x squared. And as a result, we see that since E lambda is in the unit ball, our approximate identity is assumed to be in the unit ball of A, we conclude that the norm of f is exactly the norm of x squared. Finally, part 3. To prove part 3, we define a linear map, lambda, from A to H, as follows. It takes little a to pi away applied to x. Then this map has dense range, because x was a cyclic vector. The inner product of lambda A and lambda B, well, let's calculate it. This is the inner product of pi of AX and pi of BX. Or equivalently, this is pi of B star A, X and X. So what's this? Look here. This is F applied to B star A. And finally, if we act by the operator pi of A onto lambda of B, pi of A, pi of Bx, this is equal to lambda of AB. In summary, if we look at these two lines, we conclude that we get an abstract GNS representation. H, pi, and lambda is an abstract GNS representation associated to F. And now we use our result from the previous lecture, which says that there is a unique unitary isomorphism between the respective modules, which takes lambda of A to lambda F of A. But this is exactly lambda of A. So this completes the proof. As a corollary, we see that for every cyclic star representation pi of A, there is a state F on A such that pi is unitarily isomorphic to pi F. Unitarily isomorphic. Well, indeed, to find such F, we simply take a cyclic vector and of norm 1. Of course, we can always, if we have a cyclic vector, we can always normalize it and take a cyclic vector of norm 1. And this equality implies that F is a state. So pi is isomorphic to pi F for a suitable state on A. In other words, we see that every cyclic representation is isomorphic to a GNS representation. In fact, the converse is also true. So in conclusion, I just state the respective result. And we observe that this result, the respective result, is trivial in the case where the algebra is unital. The general case will be a good exercise for you, which is not entirely trivial. So we have the following converse statement, a converse to the previous theorem. Suppose that F is a state on A, or just a positive functional, actually. Positive linear functional on our C star algebra. Then there exists a cyclic vector that's denoted by xf, a cyclic vector for the GNS representation pi f, uniquely determined by the following equality. The inner product of lambda f of A and xf is equal to f of A for every A. Let it be equality number 1. And moreover, we have the following. F of A is equal to the inner product of pi of A xf and xf for every A. So in other words, we see that f and x are related in exactly this way, like in the previous theorem. So let's observe that for unital A, the proof is trivial. If he is unital, then we simply define xf as follows, lambda f of 1. Then lambda f of a is equal to pi f of a applied to xf for every a. And the range of lambda f is dense, so this implies that xf is a cyclic vector. And clearly it satisfies both conditions 1 and 2. The uniqueness of such a vector satisfying condition 1 is immediate from the density of the range of lambda. The uniqueness follows from the density. So this completes the proof in the unital case. And the general case is a good exercise. In fact, it is much harder than in the unital case. A hint for the non-unital case is to show that we can consider the canonical extension of f to the unitization of f. And we get an isometric embedding of this inner product space into this inner product space, given by the following formula. So the point is to show, the key point is to observe that this map has dense range. Prove that if E lambda is an approximate identity, then lambda f of E lambda converges to lambda f plus of the identity. So this convergence implies that the range of this map is dense. And so this map uniquely extends to a unitary isomorphism between the completions of these spaces. So we get a unitary isomorphism. So this map extends to a unitary isomorphism between HF and HF plus. So the algebras are different, of course, if A plus is bigger than A, but the respective Hilbert spaces are identical. And now we can define the cyclic vector xf to be the preimage of lambda f applied to the identity of the unitization. This is exactly the cyclic vector we are looking for. So this is a hint. So just once again, I want to stress that this is the key observation. So if we prove this convergence, then the range is dense, and we get unitary isomorphism. So in summary, if we combine all these results, we get that for every star representation, pi of A, we have a unitary isomorphism between pi and a Hilbert direct sum of a suitable family of GNS representations, pi of Fi, and possibly a trivial summand pi 0, where Fi is a suitable family of states and pi 0 is trivial. It takes every element A to the 0 operator. This is just a combination of our previous results. So first we decompose pi as the Hilbert direct sum of a non-degenerate representation and a trivial representation. So this is non-degenerate, this is trivial, and then we decompose non-degenerate summand into a Hilbert direct sum of cyclic summands, and then we use the fact that every cyclic star representation is isomorphic to EGNS representations. So in some sense, this result means that every star representation is composed of GNS representations. So we will see fairly soon that this is quite useful. In particular, this is useful in the study of tensor products of C-star algebras. Okay, that's